Thank you, everyone. So the title, if you'd looked at the schedule, you would have seen that we were assigned some fairly vanilla titles. Mine was simply Inner Planets, and I treated that as a blank check to make the title whatever I decided, and so I moved into this. So I'm Stephen Kane, and I have been studying exoplanets for the past 25 years, but for the past 10 years, I've been working with the planetary science community to try and bridge that gap. And make no mistake, there is a gap, and that's what I'm going to be talking about today, and try and talk about the ways in which we can mitigate that, at least for the inner planets. So the extent of this gap was made particularly obvious to me when I went to the DPS meeting in Nantes in 2011, when I realized that the solar system people at that meeting, and solar system people in general, had a running gag about exoplanet people. They said that exoplanet folks are only just now realizing that there are planets in our solar system. And at first I was taken aback by this, but then when I thought about it, I realized why they were making this joke. In particular, I understood that they were only half joking, and that there are reasons behind this gap that we need to explore. So first of all, it is not necessarily intuitive to people outside of the field, and not always intuitive to people in the field, that exoplanetary science and planetary science are the same thing. But of course, they're not. And this is something that I've been working to explain to my planetary science colleagues now, that in order to understand the exoplanet community and why they sometimes have this apparent lack of interest in planetary science, you need to understand the background of where they're coming from. Because essentially, exoplanetary science is stellar astrophysics. That's what it is. So if you're a planetary scientist and you want to talk to an exoplanet person, you need to know that up front. And so you can't assume knowledge regarding things that you might take for granted. Now, but why is that? And there's a historical reason for that. And that is because, in particular, the two main techniques that have been used to find exoplanets originate from work that we've been doing for more than 100 years. And I'm talking about eclipsing binaries. So eclipsing binaries, we measure the size and we measure the mass of the companion. And we do that through the eclipses and the radial velocities. So people have been doing this for a very long time. What have we done with exoplanets? Well, we've taken this to smaller mass ratios and size ratios and pushed that as far as we can. And this is, of course, what we refer to as an indirect technique. So we're not actually seeing what we're looking for. We are studying the star extremely carefully and trying to infer the presence of an object that is there orbiting the star. And this is an important thing to understand, because when we see announcements about new planetary systems, this is a recent exciting one, TOI 700 from the TESS mission. I was a part of this, and we had a giant press release at the recent AAS meeting, and we see diagrams that look like this, showing pictures of the planets and orbits and everything like that. The thing that, once again, you need to understand is that what exoplanet people primarily are trying to do is to convince themselves and the referee that the object that they're talking about is not a star. That's what they're trying to do. And so we spend a great deal of time ruling out false positives and things like that. And so the objects that we're talking about, when you talk to an exoplanet community, they're talking about a perfect sphere of radius r and mass m. And that's it, right? So I'm stressing this because planetary science is coming from the opposite direction, and we need to meet in the middle. Like I said, there is a significant gap. The gap can be further pushed if when you show a picture like this. Typically, we see beautiful pictures, of solar system planets. This is our very, very best image of a terrestrial exoplanet currently. Now, it just sounds like I'm kicking a dead horse, and I understand that. But as I said, this is a gap which can be bridged because there are observables that exoplanet community are trying to reach, and they are trying to reach those observables with earnest. And they're not going to be able to properly interpret those without the expertise of the planetary science community. Absolutely not. And so there is a strong overlap. When we look at the Venn diagram, if we treat this as a Venn diagram, and you can see that there's no overlap, right? But actually, there is. There is overlap on this Venn diagram, and it's growing, and we need to be prepared for that, about how to address this gap and how we can cross-pollinate these two areas. So this is something which is, of course, becoming increasingly known to the AGs, and we're going to be hearing from OPAG in a moment. Vicky's going to be talking a little bit about Exopag, and I've been involved with VexAg, and with VexAg, we've been redefining our goals, objectives, and investigations to incorporate exoplanets and how the information flow can go both ways. So we reprioritized recently the three main goals that we should be prioritizing in terms of exploration, and you'll see in the first one about the Venus evolution and how that informs potential habitability. It's one of the points that I always make about Venus is that often when people are talking about planetary habitability, they'll say that we only have one data point. Everybody should always be upset when somebody says that, because we don't have one data point, we have at least two, and because Venus is showing us where the boundaries are, and that's just as important in understanding the evolution of terrestrial planets. So Noam is here. I don't think Darby is here, but there are numerous people who are representing VexAg here, and I'm hoping that there'll be some great conversations that will be happening during this meeting. So the other point I wanted to make before I go on is just a quick summary of the main points of how we move through this process of understanding the gap between the two. And that is, first of all, understanding that terrestrial exoplanets are here in large numbers. It's only going to increase. And as Vicky will talk about, these are going to be the prime candidates for atmospheric characterization. And as I mentioned, that's where the overlap for these two communities is really going to start to expand continuously. But for the exoplanet people in the room, I want to just really encourage you to try to keep up with what's going on in the solar system community. And this is I think part of the disconnect, because the exoplanet community is growing very rapidly. When I'm looking at my daily archive emails and the amount of exoplanet papers that are coming out every day, it's very, very difficult to try and keep up with that. And there is also a similar situation in planetary science. Trying to find a way to have people pay attention to the latest updates in both communities, I think, is very, very important. But as you know, there have been numerous cases where there have been advances in planetary science which have really, really surprised us. And that's, of course, part of the excitement. Now, the sobering thought that we need to bring to this is that we will never, ever have in situ data for an exoplanet. I'm sorry to say, we are not sending a lander to Proxima Centauri b, by definition, the nearest exoplanet, okay? We're not sending a rover to TRAPPIST-1e, and we're not sending an orbiter to TOI 700d. We're not doing any of those things. So what does that mean? It means that the only in situ data we will ever have will be from in here in the solar system, and we will be interpreting the exoplanet measurements up here based on our models. And our models are built from here. And so that means that we need this flow upwards in order to make this work. Now, Another point I wanted to quickly make is the axis of time, because I think this is something that we frequently neglect when we think about this as well. We, of course, are studying the solar system at the present epoch, but if that's all you ever do, then you are missing most of the information. And this is something which is incredibly important for exoplanets, because when we look at the timeline, this is a graphic that was created for a Scientific American article that Darby and Sushmika and myself published about a year ago. And they put together this nice timeline of geological activity and potential life in surface liquid water. We can argue about the specifics of this, and we should. But the point is that if we look at, say, 2 billion years ago, then there's a very, very different picture going on in the solar system. And when we look at exoplanets, we could be looking at them at any time. And so this is something that we need to think about if we're trying to leverage solar system data for use for exoplanets. All right, so now what I want to do is just give a broad picture of a couple of the outstanding questions to get the exoplanet folks and the planetary science folks in the room thinking about ways in which there could be this cross-pollination. And I'm going to quickly go through the terrestrial planets. This is not exhaustive, of course. There are massive amounts of outstanding questions. And I picked out a few from looking through the literature that I thought were the most relevant. So let's start at the very beginning. Mercury. What do we understand about Mercury? And we've had missions there, Messenger, but Messenger has revealed, for example, that the geochemistry of the surface is something that we need to understand in significantly more detail. And that's probably going to require a lander in order to do that properly. And did Mercury form with its large core? This is something that's significant for modeling the interior of exoplanets, once again, based on models from our own solar system and for planets which are very close to their stars. The cooling rate and how that has factored in to the current geology. When did the volcanic activity at the surface end, and did it have an atmosphere at any point, and when was that lost? The very early points in planetary history for all of the terrestrial planets present some of the biggest unknowns that we have to face for the solar system. And of course, I always think of Mercury and the Moon as this nice museum of impact history in the early solar system. And that's incredibly important for not just for those bodies, but for also the impact history of Venus, Earth, and Mars. So for Venus, now, as I've kind of implied, Venus is very dear to my heart. One of the reasons for this is because when I first started working on the Kepler mission back in 2008, the year before it launched, and I realized that that was the point when exoplanets was really going to be pushing deep into the terrestrial planet regime. And most of us, with the possible exception of the PI, Bill Barucki, who is a planetary scientist, really knew what we were doing. And in particular, we were going to be discovering preferentially planets close to their star, so Venus analogs. And we needed to understand why Venus and Earth are so different. There's many, many questions about Venus. Venus is inaccessible even in many ways, even though it is the closest planet. So there are a lot of questions about the history of tectonics, the interior structure, the chemistry of the Venetian atmosphere is amazingly still a mystery to us. A lot of the in situ data we have of the compositional temperature pressure profile are still from gliders, but also the Veneer emissions. And so we do need to go back to Venus. But of course, one of the reasons that Venus is so interesting is because, as I indicated on that timeline, that it could have had a habitable period up until fairly recently, as recent as about a giga-year ago. And this is profound for our study of habitability and terrestrial exoplanets. And in case any of you are wondering, wait a minute, that's not a picture of Venus in the background, except that it is. And if you're wondering why, I refer you to the timeline. So something to think about. So for Earth, of course, Earth is our best studied planet, but many, many, many questions relevant to exoplanets. As I mentioned earlier, a lot of the questions relate to the earlier stage of Earth history and the cooling rate and what that has implied for not just the geology, but the origin of life. And that's the picture of me. Oh, in case you don't know, the Zoom room is my Zoom room, which is why it has a picture of me. Let's see if I can just make that go away. Apparently no. Okay.
You keep going.
Okay. So of course the moon plays a significant role in this. The moon forming collision and the role that that has played, not just in the composition of the mantle, but the evolution of life on Earth. This is something which is coming up all the time now in exoplanets in the search for exomoons, because there is a connection that people make between the prevalence of life on Earth in the tidal effect that the moon has had on Earth over the years. The role of volatiles in continental plate subduction is a big one. When I came to the geology community and started making naive statements about, well, we know that liquid water is essential for plate tectonics, I was amazed at how much disagreement there was on that topic. And this plays into, for example, ongoing potential subduction on Venus now. And so this is something we need to think about as well. And of course, how has the composition of the Earth's atmosphere changed with time? This is essential for understanding biosignatures. Once again, the timeline. Would we recognize the Earth as a habitable planet if we obtained a spectra of it when it was 1 billion, 2 billion, 3 billion years old? Those are the questions that we're trying to answer. All right, so there we go. So for Mars is of course a fascinating object because it is showing us also limitations of habitability. What is the current state of the internal structure? We have the InSight mission there right now, but there's a lot of things that we don't understand about the interior of the planet. The transition from early to middle Mars, when it started to develop its secondary atmosphere and we had liquid water present on the surface right up until about 3.8 gigayears ago, the understanding of that transition needs to improve. We are starting to learn quite a lot in recent years about locations of water underneath the surface, but the exact nature of those bodies of water and how it relates to the geology still needs a lot of work as well. And a big one for exoplanets is how the planet interacts with the local solar environment and how the stellar wind is eroding the atmosphere. This is something which is constantly being brought up in the context of close-in planets around M-dwarfs, particularly those in the habitable zone, and something that we need to understand further. And this all leads to a question about, well, does Mars represent the lower size limit then of habitability insofar as you think about sustained habitability through gigayear timescales, or can we go larger? What are the factors that are involved there? So I want to end by just briefly talking about the pathway forward. And this is a diagram that I'm sure many of you have seen, certainly the exoplanet people would have. It's a diagram that came out for the press release of TRAPPIST-1. TRAPPIST-1 is one of the most exciting exoplanet systems to come out in recent years. And you see there's a whole bunch of mostly terrestrial planets. And then we have the solar system here for comparison. And the point I wanted to drive home once again from what I said at the beginning is that this kind of almost implies, if someone were to look at this, that we know as much about these as we do about these. Nothing could be further from the truth. So everything that we learn about these, we learn from these. That's the bottom line. And when we are able to observe these with JWST, which, as I said, Vicky will talk about, then we are inevitably going to be leveraging the models based on real data. So what is the path forward? The thing to remember is that any uncertainties that we have in solar system data, and this is why I do encourage the exoplanet community who are interested in, say, characterizing exoplanetary atmospheres to look at what the current state of planetary science is, because any uncertainties there will translate sometimes catastrophically into uncertainties in our ability to model terrestrial exoplanets. And so addressing this means going back to the core, which is the solar system sign, and this is going to require a lot of development. There is numerous mission developments going on right now. We're planning missions, another mission to Venus. There are numerous groups who are thinking about this. This is coming from both Russia, ESA, NASA. Everybody's starting to think about this because this recognition, thankfully, is taking hold. And when we're addressing these, we are, as I showed in the case of VEXAG, including the exoplanet component. So the overall message I want to leave you with is that although my initial statements make it seem very, very disparate between the two communities, there is strong overlap. It's increasing, and the way forward is to develop these planetary science missions and exoplanet missions with the common goals in mind, because the communication between the two is the only way we're going to be able to answer the fundamental questions about planetary habitability. All right, thank you very much, and with that, I'll hand over.